Okay, here we go. Students, let's get going with lecture. Uh, wow, not a lot of people. You know, I should have had a ton of clicker questions today. Exam 3, it's not graded yet. And actually, I have the clicking items almost ready to grade. I've got them broken out, ready to grade, but they're not graded yet. Same with Scantron. So stay alert over the weekend. I will hopefully get all these things graded and put together by the weekend. And then Tuesday, we'll hand back exam printouts in lecture to start lecture, and then finish out the last 2 lectures of the semester. Okay, I have a clicker question for you coming up, and it's on the topic, well, it's about this image. Our topic is electrons and atoms, and what we're trying to do is get a handle on what molecules do. That's kind of my target for the last day of the semester. And I think we'll be able to get there. We're going to work through who's got Doritos, or are those, there's somebody up, Pop-Tarts? Oh, Lord. Good gravy. Just, it automatically catches my ear whenever I hear that. Anyways, sorry to distract you. We're aiming to understand basically the periodic table. That tells us a whole amount of stuff. Now, I have a clicker question for you, and what you're going to do as soon as I open it up, you should be able to get Go Nitro right now. You're going to type in a word or two. So this is a short answer question. And here's the question. And you know what? And I'm going to grade everybody that types in something comprehensible. I'll grade it correct. Because, all right, here's a question for you. Look at this picture. I want you to look at it carefully. And type in, if you see anything unusual, look at it carefully. Do you see anything unusual? And type in a word or two using your iClicker. Let me start it. Okay, you should get, come on, baby. Hold on. Okay, you should be able to start typing in. Now hit the send key when you've typed in the word that you want to send. And I'm going to look at all of them after class. So try to give me a good 1 or 2 words. You know, you got about 14 characters, I think. So you can't write a sonnet. But you can, if you see something. And I see something that's a little unusual there. I wonder if you see it. I wonder what you see. You know, the thing about this, the thing about science is it really matters, you know, what you observe, what you see. Usually for us, it's what we see. Sometimes what we hear. I can hear all those answers clicking in. Everybody's clicking. That's very good. And you 2 guys in the back, I'm sorry I yelled at you. I should have just told you to, you know, hush. Instead of yelling at you like, I don't have any right to be angry at you guys at all. I shouldn't have done that. Ooh. Oh, cool. What? Oh, I don't know. Don't type in something that's screwballs. Type in something that's serious. You can go back and change your answer. This is interesting. Oops. I see something misspelled, but you still figure out what it is. You know, most of the answers are just one person. All right, 1 minute. And I'll try to grade everything, not right now, but at the end of class, hopefully if we dismiss a little early today. Yeah, there's some interesting. I wonder what the most. This is very interesting. 30 seconds. Ten, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Okay, let me switch over to computer. Break saw, one word. Yeah, that's what I saw. What? Check it out. That looks like a chainsaw, right? But why is he using a chainsaw on a rock, a big rock? That's what. But then, you know, the thing is, if you look carefully at those other rocks, I don't know if you guys noticed it. See this one over here? Or let me get my cursor over. Come on, cursor. See this one right here? It looks like he's already sawed through that one. You know, and then this is this is the hunk right here that is, you know, those are the two pieces. So I don't know, he might have a special kind of a saw, special kind of a blade, I should say, for cutting rock. It's possible, I guess. By the way, and make a note of this, you know the thing that's most apparent to me? I mean, I've looked at this picture a zillion times, and I didn't twig to the chainsaw thing at first. But what I did look at, and the reason I bring this up, is the beautiful green color of those rocks. This is a mineral. This is up in Canada. They took these rocks out of the mountain. You see another one in the background there, it looks like. It's known as nephrite, which is one of the two minerals that we call jade. The green color of jade is one of the things that motivates why we are heading to understand the periodic table. Now, make a note of this web address, webelements.com. Just jot that down in your notes. It's a really nice website, all kinds of, you just click on one of the elements and you can look up, its atomic number. You can look up its melting point, its boiling point, its density, the isotopes, its density, all kinds of things about, gold, copper, everything in the periodic table. It's really nice, and it clicks really good. I use it a lot. I mean, there's other stuff you can use, but that's the one I tend to use a lot. webelements.com. Now, we're not going to be talking about the periodic table much today, but Tuesday, yes. So go ahead and just mess around inside this. The reason is that we want to focus on the periodic table is that it encodes for each atom, for each element, I should say, the basic atomic structure. And what that does is encode or enforce various bulk properties of that element. And then when you put elements together in a molecule and analyze the electrons in a similar way, you can figure out bulk properties of molecules like CO2. You know, for instance, why does CO2 have a melting point that we never experience here in our atmospheric conditions? Why does it go straight from solid to gaseous? Well, that's encoded in the electronic structure of that entire molecule, which is encoded in the electronic structure of carbon and oxygen, and a double oxygen at that, CO2. So let's talk about the electrical interaction. That's our main topic for today. And get our feet ready to walk around and get our feet wet in the periodic table. Now, the theory of charge is that it's electrons. You know, back in the olden days, people knew that you could rub, you know, like a piece of amber on wool, and it would cling to something. You know, and you could do that now. You take a balloon and rub it on your shirt, and then it'll stick to your hair. You know, or you rub it on your shirt, and it'll stick to the wall, at least for a few minutes. Right? So that's static cling. You know, static cling. The dryer at home, or at the laundromat where you do your laundry. And you forget to put a sheet of, what do you call that stuff? Bounce. And, you know, all your socks stick together, right? So that's static electricity. And when you pull them apart, if the room is dark, you'll see little teeny sparks and stuff. So this idea of static cling, the guy that figured out that it was electrons behind it, his name was J.J. Thomson. There's a photograph of him. And he was a scientist up at Cambridge in England. And pretty famous guy now. He discovered the electron, basically. And he did it with an electron gun. Well, they didn't know it was an electron gun. But there's a little kind of a schematic diagram of it there below his photo. Basically, over here on the left end, you have a source, an electrical source of charges. And then here in the neck, you have some plates, some charged plates, you know, connected to a battery that accelerate whatever it is and turn it into a beam. And then you have another set of plates over here, one high and one low. Now, one of those is positively charged, and the other one is negatively charged. They're connected to the same battery. All right? So one's positive, one's negative. And J.J. Thomson said, now look, if this mysterious beta ray, you know, that's what they called it back in his day. They didn't know it was electrons. They thought it was like a ray, like X-rays. Question? Yeah, right. He's accelerating electrons. And we do it now with protons and all kinds of stuff. You're right. Only much bigger, much fancier, and now they're shaped in a ring, most of them. But that's a linear accelerator, what he's got there. Very simple one, but did the job for what he was trying to do. So here's these mysterious rays which they'd observed. And they, Maria, they didn't really know what it was. So J.J. Thomson says, I think it might be charged. It might be particles, and they might be charged. And if they are charged, and if I drive them between these two plates, one positive, one negative, it should dip upwards or dip downwards, depending on if it's positive or negative. If it's positive, it'll dip downward towards the negative plate. You know, because that's what electrical charges do. And positive attracts negative. Opposites attract, likes repel. So positive repels positive. So if it's positive, it'll be pushed away from the top plate and down toward, it'll be attracted towards the bottom plate, and then it'll light up this part of the glass screen. Now this glass screen over here on the right has some phosphorus on it. You know, just like the old-fashioned TVs, you know, the ones that have the really big TV tube made of glass, and the inside of it is painted with phosphorescent paint, really thin layers, you know, they glow different colors when they get hit by an electron. That's what he's got here. All right? And so he's got that paint. So he'll be able to tell. You can't see the rays as they're going through the glass, but you will see them when they hit this phosphorescent paint. A very thin layer. So it'll glow. It'll glow green, usually. All right? A green screen. But you know what else this is? In addition to an accelerator, this is like a TV. It's a TV with one pixel. You know, one little stream of electrons. But this is the first TVs from the 50s until about the year 2000 when the flat screens started coming out. Yeah. They were all like this. But much bigger, and with magnets, electromagnets, and a lot of different rays and stuff. But yeah, that's how it worked. Now, if this thing is negative, go ahead and write down this option. If it's a negative particle, not positive, it'll dip up towards the positive plate because positive likes to attract negative. And it'll be pushed away from the bottom plate because negative repels negative. All right? So he had a good setup here. He figured, all right, I should be able to, shoot a beta ray through there, get it juiced up good in the gooseneck and put it through as a nice tight beam. And then see which way it dips. If it dips upward or downward, it'll tell me, what I've got. Ding. There it is. It dipped upwards. The screen glowed above the line. And that means that the beta ray is negative. Whatever else it is, it's negatively charged. Now, he did a bunch of other experiments and figured out that the amount of charge divided by the amount of mass in kilograms was so small, it had to be a really, really small particle. And he has counted in that calculation the charge to mass ratio, E over m. He is accounted as having discovered that the electron exists and that it's a very small particle. All right, now let's talk about electrons and the whole concept of electric charge. Now, in the metric system, the unit of charge is called the Coulomb, and it is equivalent to the electric charge on 6.24 times 10 to the 18 protons. Now, Coulomb of charge, and you could say -1 Coulomb is the same number of electrons, because electrons are negative and protons are positive. All right? And the size of the two systems, electron charge versus metric system Coulomb, a Coulomb of charge is a lot of charge. If you've ever done any maintenance in your home or you know anything about wiring, you know that 1 ampere of charge, 1 amp, is a lot of current. And 1 ampere of current is 1 Coulomb of charge per second, through a particular point in the circuit or through a circuit breaker. And if you go above, if the circuit breaker is rated for 1 amp and there's a lightning bolt and you get a surge in your system, it goes above 1 amp, it'll melt the fuse. It'll trip the circuit breaker. All right. So 1 amp is a lot. 1 Coulomb is a lot of charge. And you can see it's a whole lot of protons or a whole lot of electrons, depending on which way you want to look at it. All right, now 10 to the 18, I don't even know what that is. 10 to the 18, let's see, 3 is 1,000, 6 is 1,000,000, 9 is 1,000,000,000, 12 is 1,000,000,000,000, 15 is quadrillion, so 18 is 6,000,000,000,000. In other words, that's a huge amount. All right, 10 to the 12, or 10 to the 18. All right, so what we normally say is, one way to think about it is the amount of charge is equal to how many electron charges you've got times how many electrons. And because the things that are going through the wire are electrons. So protons don't go, because the mass of the proton is about 2,000 times bigger than the mass of the electron. So in a piece of metal, the things that move, that carry charge, that carry current, are the electrons, not the protons. Question?
Is there like a relationship between Coulomb
Coulomb
and Watts?
and Watts? No. Only if you are thinking about a circuit with some resistance in it and stuff. I squared R, the current times the square of the current times the resistance is the amount of heat generated so like a hairdryer generates a lot of heat because there's current and resistance. You can't do a hairdryer unless you have a poorly conducting piece of metal, wrapped in a coil and all that stuff, and it takes a lot of current. So that's why you never want to drop your hairdryer while it's plugged in into the bathtub. If there's anybody in there in the bathtub, because there's a lot of current. Okay, you'll electrify somebody. Yeah, so electro-fry. So anyway, so the amount of charge on an electron, this is the other way to look at it. The number of coulombs on a proton or an electron is basically 1.6 times 10 to the minus 19 coulombs, and that's per proton. So an electron would be negative 1.6 times 10 to the minus 19. So what that tells you is that the charge on an electron is extremely tiny compared to household currents of 1 amp. 1 amp's got 10 to the 24, or excuse me, 10 to the 18 electrons going through there. And 1 electron is going to be something like 10 to the minus 19 coulombs. It's 1.6 times 10 to the minus 19 coulombs. So now, in the atomic realm, in the quantum realm, we're going to work with E. Proton is E, electron is minus E. That's called the fundamental charge. So the metric system unit of charge is the Coulomb. The electron charge symbolized E. It's the smallest one in nature, and we tend to use that as kind of like G is a symbol for gravitational acceleration at the surface of the Earth, because we use it all the time. And this one is, it's considered part of the metric system, but it's not the household level of coulombs. But and so we're going to be actually talking about electrons, protons, and neutrons in molecules. So that's why we want to talk about the electron charge. So we got to keep this in mind. All right, and we've got a lot of stuff to try to cipher out here. So let's keep going. Now let's talk about what the modern theory, what we know about protons, electrons, and neutrons. Okay. We know that the electron is negative, and a few years after Thomson discovered the electron, another individual discovered the proton, and so then they thought, okay, if there's a proton, and the person that discovered the proton also discovered the atomic nucleus and where all the protons are. you know, they figured out, well, it's got to have some neutral stuff in there, but they couldn't find it. They couldn't measure the neutral particle known as a neutron now till about 30 years later, 25 years later, I guess. So here's a bindle. Here's a nucleus, 2 protons, 2 neutrons. Here's some electrons. And the electrons orbit out there. We'll be talking about electron orbits. This is helium. The atomic number for helium is 2, which tells you how many protons are in the nucleus and how many electrons in a neutral helium atom. Now, if helium gets ionized, you know, if somebody comes and steals, you know, like a photon comes in and zaps that electron out of there, then you just have 1 electron, but you still have 2 protons. You got a positive helium ion, okay? Which, you know. So, but if you have a neutral atom, no, not an ion, neutral atom, it's 2 electrons, same as the atomic number, and 2 protons, always 2 protons. And my wonderful students, make a note of this. In the periodic table, the atomic number, the number of protons, controls the chemistry. All chemical reactions for a certain element are basically controlled by how many protons in the nucleus, because that controls how many electrons it likes to have in its neutral state. And so, you know, you could have any number of electrons attracted to an atom, but in a neutral atom, that's where nature likes to be. It's whatever the number of protons is. All right. Now that's a little nugget about the theory of charge. Let's talk about charging mechanisms. Okay, so this is a picture of a young lady combing her hair. Yeah, friction. You know, same as your socks in the dryer. You know, if you don't have that cling free in there, you know, all that friction, you know, rumbling back and forth is going to, you know, cause a lot of frictional charge. And so what tends to happen is her hair tends to become positive. The comb strips electrons from her hair, from her strands of hair, and just holds on to them. Now, the comb is made of plastic or something, right? Okay, so it's an insulator. It's not going to conduct those electrons. If it grabs an electron or two, they're just going to stay there. They're not going to be conducted. You know, a conductor, like a piece of metal, they're going to move somewhere, you know, from left to right or from top to bottom or something. But if it's, you know, like a plastic comb, it's just going to sit there. So she can build up charge on her hair because now her hair has a net positive charge, Alexis. Okay, because it's missing electrons. And the comb's got a few extras, so it's got a net negative charge. So that's how that all works. Another way you can charge things up is by doing a little bit of friction and then touching another object with the comb or, you know, with whatever you've charged up. Okay? Now, this whole idea of friction, somebody has made a bunch of measurements and arranged everyday materials into a stack or a list called the Triboelectric series. And this is, from top to bottom, the stuff that if you rub it, it will tend to become one or the other, positive or negative. So if you rub rabbit fur and hard rubber, that's down the bottom half, you know, or if you rub glass with saran wrap, you're going to develop some electric charge, okay? So glass and rubber, positive and negative. So one of the guys that figured out a lot of that is Ben Franklin. By the way, Ben Franklin is the one that decided that the stuff that goes on the glass he was going to call positive charges. I mean, they could have called them red and blue. They could have called them black and white. They could have called them any number of opposite kind of things. They decided to call them positive and negative. The reason the protons are negative is because of what Benjamin Franklin started. He did a lot of the early electrical work over here in the States. Another interesting guy is this guy, James Clerk Maxwell. And this is a big diss on mathematicians. He's the one that figured out the theory of the electromagnetic field. Before the days of Maxwell, before the days of Franklin, really, people knew that there was magnetic forces. People knew that there were electrical forces, but they didn't realize that they were part of the same interaction. And he had this famous saying, mathematicians may flatter themselves that they possess new ideas which mere human language is as yet unable to express. So he's saying that the math department thinks that only they can understand certain things because they have to be expressed in mathematical symbols. Let them make the effort to express their ideas in appropriate words without the aid of symbols. In other words, to write it in a sentence. And if they succeed, they will not only lay us laymen under a lasting obligation, but we venture to say they will find themselves very much enlightened if they can do it. They will find themselves very much enlightened during the process, and will even be doubtful whether the ideas as expressed in symbols had ever quite found their way out of the equations and into their minds. So what he's telling the math department. See, he was a physicist. He wasn't a math. He was a skilled mathematician, but he was a physicist, at Cambridge, and he said basically here that the mathematicians have no idea what they're talking about when they write down all these equations. But if they can figure out what to say, what to write, they might actually know. And Maxwell wrote the book. Underline that. If you know nothing else about Maxwell, he wrote the book on the electromagnetic field. I mean, we're still studying his stuff to this day. Every grad student in physics just got to learn Maxwell's equations. Let's keep going. Another way to acquire charge is to polarize something. And so what that does is take comb your hair and charge that up, and then bring that next to a neutral piece of paper that you haven't done anything to. Matter of fact, I think this is how photocopiers work, if I'm not mistaken. They charge up part of the machine, and then the paper acquires charge only where you want the letters to go. I think it works that way. Anyway, so polarization. The polarization means that all the protons and the electrons in the paper, when it's neutral, when it's just sitting over there and you haven't brought it over near your comb, your charged up comb, it's sitting over there, the protons and the electrons, they're just evenly distributed. And they're not reoriented or anything. It's, they're just pointing every different which way, and, it's all discombobulated. And so there's no net electrical effect. But if you bring it close, the positives will be attracted to the comb. The negatives in the paper will be repelled from the comb. And so you'll set the top of this little piece of paper here, all right, the top will be positive, the bottom will tend to be negative, and you'll have separated some electrical charges. And here's one thing you can do. You can do this at home. You take a comb, you charge it up, you run it through hair or you scuff it up on your shirt or whatnot. And then you turn on the faucet in the kitchen to the thinnest. You can't do it with drops, but it's got to be a stream. So the smallest possible, flow in the faucet that is more than drops in just a continuous stream like this. All right? It's kind of tricky to do, but it's not that hard. All right? And then you bring the comb next to it, and what you find is the water, instead of going straight down, it kind of dips over to the right or wherever you're. So there's a net pull force. Look at that. Look at it. Look at it. Don't look at your phone. Look at the diagram. Don't look at your phone. Don't look at your computer. Look at the diagram. Come on. Green t-shirt man. Right. Look at the diagram. All right? You do that with a comb, you're going to get a net force towards the comb. And the reason that happens, it's kind of like this. Every few molecules of water are going to get polarized. All right? Because water is a molecule. Water's not symmetric. CO2 is two oxygens and a carbon in the middle. But water's kind of triangular, H2O. It doesn't have a nice even shape. It's kind of an angular. And they'll get reoriented, and then you'll get a net pull. And this paper back here on the previous slide, that paper, that little slip of paper, now that's a pretty big slip of paper, just for demonstration purposes, for illustration purposes. But if you take a little tiny slip, you tear up a piece of paper, good and dry, and it's a little tiny pieces, you can pick them up with a comb. And by polarization, same thing here. You get that net force to the right, from each and every molecule, zillions of them. And hey, you guys, that shape of the water molecule that permits this is controlled by the electrons in the hydrogen and the two hydrogens and the one oxygen. All right, so that's why we're trying to understand the electric field. All right, so the electric field. Now, you ever seen a picture like this? It's called a Van de Graaff generator. Here's another picture. And usually, on the internet, it's usually girls with long hair that do this. But we've had that in class. I'll try to bring it on Tuesday. We've had it in class, and you never know whose hair is going to do a good job. But my hair is a little too short right now, so you won't notice it. But if you're in class on Tuesday, I'll try to get it over here, and we'll try to demonstrate it. And it's pretty funny sometimes. But we could do, and that's the electric field. That silver metallic sphere, it's aluminum. It's filled, you see that post? That post is basically inside that little post, the kind of yellowish post, right here and right over here. It's shielded, but there's a little conveyor belt in there. That's all it is. A little cloth conveyor belt and a little motor. And it's triboelectric. It's frictional. But it deposits charge onto that metal sphere, and quite a bit. Matter of fact, accelerators, this Van de Graaff generator is still in use, big ones, as accelerators to study subatomic particles. Right? Now, this is one for the lab. But you can, I've seen demonstrations of the Van de Graaff generator, and you can see it on YouTube. Just type in Van de Graaff, and you could see lightning bolts. Now, we don't have anything that big here at UCF, but when I was in grad school and I was teaching a lot of classes, we did have one that stored up a huge amount of charge, and then you connect the two metal spheres. In other words, you don't use a human for it. You connect two metal spheres, and you get this big blue, lightning bolt between them. It's amazing. So let's talk about electric field lines. All right, that thing's loaded with positive charge. All right, and you can set it up so it's loaded with negative charge if you want. All right, so let's say that the field lines are just like that girl's hair. They're pointing away. The strands of hair go flying out into the universe like that because of some F equals ma. the field lines tell you the direction of F equals ma for another positive charge. So the electric field lines, if the sphere is positive, the electric field lines point away. All right? Because that's the way another little teeny positive charge would move. All right, so draw yourself a sphere, a circle to represent a sphere, and load it up with positives, and kind of make them evenly distributed like I have. And then write a bunch of lines. How many have I got here? 1, 2, 3, 4, 5, 6. I got 12 lines here, right? And a nice even number. But try to make them symmetric, and just give them each an arrow that moves away from the positive charge. Because if you were to put a little positive charge like out here where my cursor is on this field line, it would move out to the lower left because positive repels positive. All right. Now, by the same token, let's go to the next one. A negatively charged, we could do this. Negatively charged sphere, yeah. So put a bunch of extra electrons out there on the surface, because that's where they'll tend to accumulate on a metal sphere, out on the surface, the outer surface. Now here, if you put a little teeny positive charge out here somewhere, it'd want to go towards the electrons, because opposites attract. So the field lines, if you have a nice sphere, everything's symmetrical, the field lines will also be symmetrical, at least for a few inches, a few centimeters. Then it might get interfered with by the wiring in the ceiling or something like that. But yeah, at least for a few inches, you're going to have symmetrical inward field lines. All right. So this hypothetical positive test charge that we call the test charge, it tells you the direction of the electric field lines. All right, and the electric field lines are actually the things in electromagnetic radiation, light, infrared, X-rays. These are the things that are wiggling, the electric and the magnetic fields. Now, we don't have the magnetic field set up here, but we could do that if we wanted to. But these are the field lines that wiggle in radiation. There's wiggles. So there's wiggles. This is the equilibrium setting of the field lines. But if you accelerate those electrons in the surface of the sphere, counterclockwise or clockwise, jiggle them back and forth a little bit, then you'll get wiggles in the field lines, because the field lines will, reorient themselves. And those wiggles travel outward at the speed of light. Now, what if you have a positive and a negative together? That's called an electric dipole. So draw a negative sphere on the left, it's blue, and a positive sphere on the right, it's red. That's my traditional color choice for positive and negative charges. Electrons are blue. My old chemistry teacher, Dr. Cooper, in high school, he always said, electrons are blue. So now I always make my negative stuff blue. Now, if you look at this, and I don't know how you can sketch this, but let me walk you through this. In close to the negative, the field lines are inward and they're symmetric. In close to the positive, they're outward but symmetric. But now when you get away from the positive over here, they're slanted. Out here, you're not at a symmetry point. You're getting a little bit of slant, because you're getting a little bit of attraction from the electron, from the negative, the blue one, and a little bit more repulsion from the red positive charge. So up here you got kind of a mixture. Now over here, right down the center line, look at this. All these arrows are to the left, because on the exact center line between the two charges, between the positive and the negatives, you have as much attraction as you have repulsion, because every point here is the same distance if you're right on the center line. Now, if you're over here to the left or over here to the right, you know, you got some of this bending. Okay, so it's not, but right here on the center line, yep. Now, right here on the horizontal center line, the lines go straight in to the negative and straight, and then over here they go out of the positive and they go straight across. And then over here to the far right, they go out of the positive and straight off to infinity on the right. But everywhere else, it's going to be curved around. Now here's another picture. Okay, and these are actually the field lines now. All right. And so now here's the reason that a dipole electric field is important. The effective electric field of the water molecule is dipolar, because we have a positive end of the water molecule and a negative end. The positive end is the triangular part where the hydrogens are. The negative end is the corner where the oxygen is, H2O. All right, so it's going to have an electric field that, you know, in close might look symmetric around the protons and symmetric around the oxygen, but if you're a fairly good distance away, it looks like this. All right. And there's other fields. You know, there's something called the quadrupole field and the octopole field. But this is the one that I want to emphasize for now, because this is helpful for studying water, among other things. Now, let's get down to electric charge interactions. And just to review, charges in matter, it's an inseparable property. The electron will always be negative. The proton will always, it's considered a property of a proton. In other words, you know, a proton can have different velocities, but it can only have one electric charge, plus 1 e. An electron can go at the speed of light or 2 miles an hour. You know, an electric circuit, you know, the interesting thing about the electric circuits everywhere, the electrons aren't really moving very fast anywhere, even in a direct current. The speed is pretty low. Definitely not the speed of light. But they start moving pretty quickly. That's why things turn on really quickly, as if it's the speed of light. But anyways, so you can have any kind of velocity you want up to the speed of light, but you can only have one charge level. It's a quantum property. So electrons are negative, protons are positive. The electric force is basically this: like charges repel, unlike charges attract. Now, I want to add some variations to that, all right? And the variation is basically ions. A neutral atom has equal numbers of protons and electrons. So this pink rectangle on top shows something with 3 protons in the middle, 3 electrons on orbits. Okay, 3 minuses. Those minus signs in parentheses represent electrons. And then in the center, there's 3 plus signs. So that, students, you can write that down. This is a lithium atom. It's a neutral lithium atom in the rectangle on top, the pink rectangle. Now, the kind of brownish-orange rectangle, yellowish-brownish, say you strip off that outer electron. That's the easiest one to strip off. That oxidizes lithium. Lithium dioxide. Dilithium crystals. There is such a thing as lithium dioxide. All right, so you strip off, or dilithium oxide, I should say. You strip off that outer electron, now you only have 2, but you still have 3 protons in the middle, so your net charge on this ion is positive 1. All right? Now that is really important. That is how a lot of the things in the periodic table bind to each other. A lithium and an oxygen will bind because the lithium loses an electron, and guess who gets it? The oxygen. All right? And that's what we call an ionic bond. So an ion can be positive, or it could be negative. Here's a dark pink. Up here is the lithium down here, neutral lithium. And what if you jam in a 4th electron? Yeah, we can do that. It's not easy to keep it, but we can do it. You ionize, you jam in an extra electron in there. And so now that thing's got 4 electrons, so minus 4e. And then the nucleus is plus 3e, so the net charge is minus 1e. So we call that a minus or a negative ion. And this would be a negative lithium ion. Now, Mother Nature likes the positive lithium ion. It likes to work with those. It likes to oxidize lithium. All right? And so the 2 ions, these 2, they could interact. A positive will attract a negative. All right? And so here's another ionic substance bound ionically. Sodium chloride.
Unknown caller.
Sodium chloride. Sodium, if you expose sodium to the air, the moisture in the air will cause sodium to explode. And you know what? My high school chemistry teacher, Dr. Cooper, on one time he dropped it, or he had a chunk of sodium and blew himself across the lab. They had to call the fire department, evacuate the high school. It was excellent. We got to skip class for the rest of the day. But Doctor, he was a tough old bird, so he was all right. I guess he got some bumps and bruises, but yeah, sodium. Destructive, it's explosive. Chlorine. You know what these jerkwads over in Syria, they just dropped chlorine gas over there supposedly. A weapon of mass destruction. The last time they used it in battle, in combat, was World War I, 100 years ago. They were using chlorine. They just developed, the Germans figured out how to use it. They developed the process for getting chlorine by itself, and they used it as a weapon, and it killed and maimed a lot of people. It basically fries your lungs. So you can be asphyxiated or permanently have lung damage from chlorine. But yet, sodium chloride, NaCl, sodium loses an electron, chlorine grabs it, they bond together, negative or a positive sodium ion and negative chlorine ion, and what do you have? NaCl, salt, the salt of the earth, the stuff that we need to live. You can't live without sodium ions in your body. Is that right? Sodium ions? Biology, if Darian were here, biology major, is it sodium ions or chlorine ions? Sodium, for the ion pumps and all that stuff? Yeah, sodium and potassium, yeah. You need a bunches of different, ions. But anyway, so sodium, you need it. Sodium by itself, explosion. Chlorine by itself, weapon of mass destruction. But NaCl, and you know what that is? That's electrons doing their thing. Electrons interacting. In this case, with the sodium, the missing electrons. So that's an ionic bond. All right, electrical conductors and insulators. A conductor is anything in which the electrons are relatively free to move. Now, in copper's a good conductor. The electrons, it does take a little bit of work to move them. They're not totally free and loose. But there's 1 or 2 conduction electrons in a good conductor. and they're relatively, so you add a battery. And if you're working with copper, it doesn't take a lot of voltage. If you're working with something that's not quite as good of a conductor like aluminum, aluminum will conduct, but you need a bigger battery. A little more voltage, right? So the thing with electrical conductors is if you add charge, it'll dissipate, it'll run away, because the charges will repel each other. The electrons will repel each other, and they'll chase themselves out of the picture. All right? They'll try to get themselves as far apart as they can. So stuff like metals, graphite, which is a form of carbon, anything that has ions, any kind of solution that has ions in it. Example of that is the famous citrus battery pictured here. You put a piece of copper and a steel paper clip and jab them into a lemon, and we do this in class some semesters. And then you hook the copper and you wind the wire around a compass, and then you attach it to the steel, and what you see is that current flows through the wire because the compass needle moves. Why does it move? Because of the electromagnetism. Those coils around the compass turn into an electromagnet, and the compass magnet detects that. Question? Yeah, but that's right. Bananas. A lot of fruit. I've seen it with potatoes. In fact, I think we've done it with potatoes here at UCF. Matter of fact, I think there might be a YouTube of a citrus battery. I know I've recorded it with students and gotten photographs of it. Insulators. Electrical insulators. Now, this is stuff where the electrons, you can move them, but it's harder. All right? So, in other words, it takes a lot of voltage, maybe even more voltage. It might start to burn before the current starts to move, so if it's a good insulator. So, as I said, the charges, if you put any charges on there, they tend to not move and just stay where they are. So that means that a conductor, you can make, if you can do it, you can make a positive end and a negative end, and they'll stay that way. Versus a conductor, you can't, because any charges that you put in there, they won't stay where you put them. They'll redistribute themselves out to balance out the voltage and the forces and stuff. All right. So examples of insulators: glass, wood, diamond. Diamond's actually an insulator. Carbon graphite, conductor. Carbon diamond, insulator. Relatively speaking. Now, third class, semiconductors. And this is where, your electronics. Unless you have an old radio with glass, what do they call it? Vacuum tubes. They look like light bulbs, but they're really doing the same thing that a little transistor made of silicon does, in which you get millions of them per square millimeter in a piece of electronics. So what these do, they conduct or insulate depending on the circumstances of voltage. So if you put a voltage across it, it'll go from insulator to conductor or vice versa, depending how you have it set up. And so applications of that are like computer chips, solar cells, stuff like that. Okay, now I want to go through some material about the electromagnetic interaction. And the electromagnetic interaction is named after a man named Charles Coulomb. Charles Coulomb from France is the guy that figured out the force law, just as Sir Isaac Newton figured out the force law for universal gravitation. Now, he was a little bit after Sir Isaac Newton. He started out as a military engineer down the French island of Martinique. Then he moved to Paris, became an academic scientist. And it's there's a stamp from France, or I guess maybe Spain. No, that's France. He developed a balance, and not a balance that tips up and down like a seesaw, but a balance that twists, a torsion balance we call it. It stayed horizontal but twisted horizontally, and the twist angle correlated to force. So if you have a regular balance, the amount of twist, the amount of dip you get depends on how much mass you have. Right? If you have more mass on one side, it'll dip to that side. Now, for what Coulomb did is he had one where the two arms of the balance rotated depending on the force that they experienced. So what he did was use his torsion balance to figure out, all right, for static electric charges, what's the distance dependence between them. And he measured it out and he found the pattern, and it turns out that the pattern is the same as, I shouldn't say same as, very, very similar to universal gravitation. First of all, it's pairwise, charge to charge. So here's a positive and a negative. They're attracted. It depends on the distance. Okay, so it depends on how much charge you have. In other words, how much do friction do you apply, charging up your balloon, or, however you're charging it up. It depends on the distance, and it gets weaker with the distance, and here's the formula. Conversion constant K, that's known as Coulomb's constant. Q1 and Q2, those are the symbols for the electrical charge on the two objects, whatever they happen to be. It could be 0.2 coulombs on one of them and negative 3.4 coulombs on the other. Okay? And then you multiply those two together in the numerator, and then you multiply by K, and K is a constant. And then you divide by the square of the distance that separates them. All right? So now the thing is, and he figured all that out. He figured out, whoa, another inverse R squared force. But it's different because there's two kinds of electric charge. The only kind of force that you get with universal gravitation is attraction. You don't get any repulsive gravitation unless you're in a Hollywood movie. All right? But in the Coulomb interaction, you can get charges that repel each other if they're like. And of course, you get charges that attract if they're unlike. All right, like the diagram. All right? So the charges don't measure in kilograms. So that constant K up there, it's known as Newton's constant. It's 9 times 10 to the 9 in the metric system. It's fairly easy to remember, but you don't have to worry about memorizing it. I just know it because I use it a lot. 9 times 10 to the 9, and it involves coulombs, meters squared, and newtons. But basically, just try to remember attract and repel. Now, we're going to do a clicker question here. Let's see if you guys are thinking. Okay. Now, I want you to look at this. Go ahead and make a sketch. Top pair, we're going to go pair by pair. Upper pair is 2 electrons. Middle pair, a proton and an electron. And then the lower pair is 2 protons, plus 1e plus 1e. All right? And as before, blue denotes negative, red denotes positive. Question. Which pair or pairs have a repulsive interaction? Top, middle, bottom, top and bottom, or all three? Go ahead and vote. Okay, 15 seconds. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Okay. Oh, yeah, 87% of you got it right. Top and bottom. Yeah, because the top and bottom repel. 2 electrons, bing, they repel. Two protons, bing, they repel. Now, if they're the same distance apart, which they kind of look like they are in here, the newtons will be the same. The newtons pushing the electrons apart, same as the newtons pushing the protons apart. The difference is that protons are about 2,000 times more mass. So they get the same force electromagnetically, but they don't get the same acceleration. Right, next question. This one's a brain burner. Net force on this one on the right. So I'll put my cursor over here by the rightmost proton. What's the net direction?
42.
Yeah, so it's basically a... So talk to your neighbors, talk it over. This one requires a little bit of thinking. Is it rightward, is it leftward, or is it 42? Better not. Dude, who voted for 42? Okay, good, you just changed it. Michael Bacon, was that you messing with my mind?
Not me.
Somebody's a Weisenheimer. Boy, I hate raising my voice like that with students. I apologize to you. Starting off the class like that. All right. You guys are kind of inching along here. Let me give you 20 more seconds to talk it over. Starting right now. You can change your answer if you want. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. Zippity doodah. Yeah, you guys are geniuses. Right word. Look, here's what you got to remember. Think about it. Okay? You're trying to figure out the force on this one. Okay, now it's going to get some rightward newtons from the proton in the middle. The proton in the middle is closer. So the rightward newtons are pretty big. You know, whatever they are, they're a big number. Now this one over here, this electron, that's going to give you some leftward pullback newtons. It's going to, you know, this electron is over here. It's going to try to get this proton over here to go to the left. But it can't do it because it's twice as far away. So it's got some newtons, but 4 times or 1/4 as many as this one provides. So the net force is to the right. Now, why do we want to study interactions like that? Well, we're trying to figure out stuff like this molecule, retinal. Retinal, you know, retinal is an amazing molecule. It is the molecule in your eye that allows you to see. When it's hit by a photon of light, it bends and kind of twists. And then it restores itself, goes back to its baseline configuration. And it gets hit by another photon of light, and every time it gets hit by a photon and bends, that triggers the optic nerve. And then inside your brain, all those signals are interpreted as vision, color vision. And we'll get to that on Monday or on Tuesday. Start reading into chapter 10. Go ahead and start. Just start skimming. It's good. We'll see you next week. You're dismissed.